Matter. It's the stuff that makes up the universe and everything in it. Galaxies, stars, planets, you and me. Atoms of individual elements are the building blocks of matter. Inside atoms are protons, neutrons, and electrons. Inside protons and neutrons, we find quarks. An element is defined by its atomic number or the number of positively charged protons in its nucleus. Nitrogen has 7 protons, hydrogen has 1, and potassium has 19. If these atoms had a different number of protons in their nucleus, they would no longer be that element. They would be a different element. But what about neutrons? Neutrons don't have a charge. In the nucleus, they allow the protons to exist very close together. They have about the same mass as a proton. Atoms can have a different number of neutrons in their nucleus and still be the same element, but with a different atomic mass. These varieties of different atoms of the same element are called isotopes. Well, that's interesting, but who cares about isotopes? Why do isotopes even matter? Enter Jessica Miles, a student at the University of Michigan. Far away, Jessica has been working around beautiful Kongsfjord Glacier in Svalbard, Norway. And what is Jessica doing up there? Pulling up mud from the water in front of the glacier and scraping mud off of the icebergs coming off of the glacier. And packing up samples of mud that she's going to take home with her all the way to Michigan. Why is Jessica so interested in mud? Well, because mud is matter, and it is made up of atoms. And inside these atoms are protons, neutrons, and electrons. And some of the elements of those atoms in the mud have different numbers of neutrons. They are isotopes. Specifically, Jessica is looking at isotopes of 2 elements, strontium number 38 and neodymium number 60. Let's check in with Jessica to find out why. So today I have Jessica with us, and she's going to tell us a little bit about the research that she's doing here in Svalbard with the REU group. So I have a couple of questions that I'm going to ask Jessica. The first, Jessica, is there are isotopes of lots of different elements. So why are you specifically looking at isotopes of strontium and neodymium?
Well, I think it's really cool that when you're looking at isotopes, you go out in the field and you have mud and water samples, and then you end up getting just like one single element out of it. And then I'm interested in looking in strontium and neodymium because strontium tells you about the chemical composition of a glacier, and neodymium tells you about the age of the bedrock.
Wow. So. Yeah, I think that's really cool too, that you can take sediment out of water in front of a glacier and figure out information like that. You can't really see atoms. How are you going to find these isotopes of strontium and neodymium? How are you going to see them?
Well, hopefully, once I get back to Ann Arbor, I will run my samples through column chemistry, and then I'll end up getting a sample that's about the size of a grain of dust, and I'll put that on a mass spectrometer, and that will be able to give me a more holistic view of what's happening in the glacier.
All right, well, how did you get interested in these isotopes, specifically strontium and neodymium? What attracted you to studying isotopes to begin with?
Well, strontium and neodymium I think are really cool because strontium is, the levels of it in a glacier vary depending on the type of bedrock. So there's silicates and carbonates are a lot softer than silicates. So with carbonates there's a lot more strontium levels. And so then it kind of tells you how, like what kind of bedrock the glacier is sitting on. So I think that's really interesting. And neodymium I think is cool because it tells you how old the age of the bedrock is, so you can tell how much a glacier is melting down the bedrock, and then you can know more about like how global warming is impacting these specific glaciers.
So just by looking at a ratio of strontium isotopes, you can differentiate how much of the rock is carbonate and how much is silicates?
Yeah.
So what are you going to do with this information once you have it?
Hopefully, I will be able to understand a little bit better what's happening in the Kronebreen glacier, and then I'll be able to look at that and kind of do a compare and contrast between the one in Alaska with Lemon Creek, and so I'll be able to see if the same types of things that are happening at Lemon Creek are also happening up here in Svalbard.
So see, isotopes are important, and this is only one of the ways that they are used in science. Thanks, Jessica, for sharing your research with us, and good luck.